Do you guys remember the hovercraft problem from last year? Remember that hovercraft problem? This thing is even cooler than the hovercraft problem. This is like, this requires all mathematics that you've ever used in your entire life. It's so cool. The only thing it doesn't have is logarithms. Yeah. It has complex solutions, so it's the possibility that they could be imaginary or not. So it's pretty cool. It's pretty cool. All right, so a piece of tin, 24 centimeters wide, will be folded to create a gutter with a base that is 10 centimeters and sides that are 7 centimeters. If you watch this problem from 2 years ago, Kyle Ohms was in class, and he was having a really bad day, and he couldn't stop nagging on the fact that we were doing a gutter problem. He's like, this has no point. I'm not going to be installing gutters in life. Like, when, you know, yeah. Kyle's gutter service. So anyway, so if you're watching, Kyle, they actually did. So Addison Peterson, remember Addison Peterson? Great student. And then Kyle and then Colleen, they came to see me right before Christmas break, I think, or was it Thanksgiving break? Christmas break. And they said on their way, and they were watching on their phone my YouTube videos. So just to hear my voice again. So anyway, so it's kind of creepy. All right. So a piece of tin, 24 centimeters wide, will be folded to create a gutter with a base that is 10 centimeters and sides that are 7 centimeters. Both sides will be folded at the same angle. What angle should the sides be folded in order to maximize the amount of water the gutter can hold? Oh boy. Got it already? I'll be honest, you guys, this is a type of problem that the teacher says I should really do this before we do it on the board. And I have. I've done it the 2 previous years, but I did not just do it last prep hour. And instead I made that. Yeah, so I probably should put that on YouTube. So, all right, here we go. Let's do it. Okay. There's your piece of tin. 24 centimeters. So the whole idea is that we model the problem first, right? Yeah, so let's do it. Let's fold it. And so we fold it. You don't really, well, I guess we'll take the top off, okay? It's a convertible. All right. So this is 10, that's 7, and that's 7. Does that add up? 24? Okay, so if we left it flat, where would the area be? 0. The area is 0, right? Okay. So what you want is you want to maximize, it says maximize the amount of water, so we want to maximize the area, right? So, yeah, we got a trapezoid. Very good. Very good. Well, hopefully. I mean, it's kind of a complicated problem, right? So the question is, what angle should we fold it? And would you guys agree that as I fold this up, okay, hopefully the area, you know, increases until some point, you know, the area is at its maximum. Obviously, if I folded it all the way over, it would be back down to 0. So you can see as theta changes, the area changes as well. So what should we do? Okay, let's do that. Equation for a trapezoid, we can do that. So area equals, and I really am trying you guys to just take insights from you and build off of it, as opposed to just show you the quickest way to work through the problem. So we're on the right track here. Area is equal to 1/2 times the height, B1 plus B2. Yeah, we don't know the length on the top, do we? Let's just draw a segment so at least we have a length on the top. I'll draw it in blue, because I don't like dotted lines. What you think? What you think? What you think? Oh, does everybody see what Brooke is doing here? Okay, this is a really, really good idea. Okay, Brooke is saying that she would like to create a triangle. Now, there's two triangles that can be drawn, and this is really the way that the problem gets generated now. So she wants to take and drop down an altitude, as we call it, or you could look at this triangle right there. Okay. Now, obviously, in this situation, she's now created a triangle where she has theta. That would be, the measure at which we would fold it. Okay. But I'm also going to talk about this angle right here. For the sake of not using the same variables, we'll use beta. Okay. Okay. All right. So, what now? Do some trig. All right. Great idea. Awesome. Okay, but why do some trig? You see theta, so it's like it's got to involve trig. That's a very good idea. You're absolutely right. But the question is, why are we going to use it? What do we need to set up? Where are you at? Yeah. If you look here, okay, so I'm going to tie all these things together that you've kind of been thinking and that Emma's been saying here as well. What is this length right here? That's 10. So I'm going to call, this x and this x, right? And then I'll call this height, sure, or y. Yeah, yep. That's fine. You're absolutely right. H would be fine. Okay. I'm just going to call it y for this scenario. So right now, if we were to put everything in there, look at what we have. Area is equal to 1/2 times the height, which is y, times base 1, which is 10, plus base 2, which is 10 plus 2x, right? But the fact is theta involved in there at all? No, it's not. And that's problematic, because we want to solve for the angle. And so instead of having y and instead of having x, let's solve for them so they're in terms of theta. Okay, let's solve for them so that they are in terms of theta. So, what kind of triangle? 90-degree triangle, right triangle. And so, what kind of trig principles can you use with a 90-degree triangle? Yeah. Sure, law of sines work, also just SOHCAHTOA, right? We can set up SOHCAHTOA. Sine is opposite over hypotenuse, so on and so forth, right? So let's just look at our angle right here. We know that that is beta. We're going to be working with beta in this scenario right now. We could say beta and y and 7. Which trigonometric function has to do with beta, y, and 7? Cosine. Very good. So we are going to make a couple statements. Cosine of beta is equal to what? Y divided by 7. Or in other words, 7 cosine of beta is equal to y. Well, hey, I got rid of my y piece, haven't I? Now, let's look at x. Which trig function do you use for x? Sine. Sine of beta is equal to x over 7. So 7 sine of beta is equal to x. Well, golly gee. The rest is mere algebra, my friends. Let's write it out. Area in terms of, what is my variable? Beta. So we just did box 2, right? That's what we did. We drew box 1, okay? Box 1, we drew the figure, and then box 2 is this connection piece right there, the formula and the trig setup. So that's the most difficult, right? And that's what we worked through. But I did it so that I could get one variable. I've got beta, so area in terms of beta is equal to 1/2. What is the height? 7 cosine beta. Times parentheses. What's base 1? 10 plus 2 times 7 sine of beta, which is because we have the 2 x's on top, right? So we've got x, which is 7 sine of beta, x, which is 7 sine of beta, is 14 sine of beta plus the 10. So, wait a minute, why do I have 2? Oh, yeah, 2 10s. One's from the top, one's from the bottom. So that's why I've got all that. So, are we okay with this? Okay? No? You're great. All right. So, let's work this through. Area in terms of beta is equal to, I'm going to leave the 7 cosine of beta and the 1/2 outside for right now. And, well, no, let's get rid of that 1/2. Let's just get rid of it. Okay? So 7 cosine of beta, let's distribute the 1/2. 10 plus 10 is times 1/2, 10. Plus 7. Everybody okay with that? Okie dokie. So, that's my function. You got 2 choices right now. You can either leave it like this, or you can distribute the 7 cosine of beta through. What do you want to do? It doesn't matter. Okay. What? Well, if I take the derivative right now, I would use the product rule, right? Okay, we'll still have to use the product rule. So, 70 cosine of beta plus 49 sine of beta cosine of beta. Everybody okay with that? Okay, so we have our function. What's our goal? Maximize the amount of area, okay, and therefore we take the derivative and set it equal to 0. Isn't it? Just think about what you said. You said take the derivative and set equals 0. Remember how long we spent trying to take derivatives of things? You know what I mean? And now you see how powerful it is. Like, you want to maximize something? Easy. Take the derivative. That's cool. That's cool. So, let's do it. The derivative set equal to 0. 0 equals, what's the derivative of 70 cosine of beta?